Okay, this problem we have a mass spectrometer, and I'm going to start just by kind of talking you through the mass spectrometer first before we launch into the problem. So in the written problem, there's a huge description. I decided not to rewrite that here. What we have is notice that there is a potential difference that's given there, and there's an ion source. So this is just some kind of charged particle, and the particle would have, some charge Q, some mass M. Fine. Um, then accelerated through this potential difference here, right? So accelerated through the potential difference and then enters a magnetic field. And what the magnetic field does, of course, is changes the direction of the particle. So notice that B here is shown to be everywhere out of the page, right? So what that means right away to you, you can kind of go like V cross B, what types of particles are even going to be directed to the right. So think about what charges. Already you're doing some filtering of charged particles. So if it has a particular charge, then one particular sign, it will curve off to the right. If it has the opposite sign, it'll curve off to the left. And I'm going to leave that to you to think about there. You can also get a clue from looking at the polarity of the potential difference, which is when we have that potential difference, that's essentially an electric field that we've set up there. So the particle curves and hits some spot in the detector, and the spot it hits in the detector, notice that this is basically the diameter. This X here is the diameter of its path. So that detector would be connected to a computer, right? The detector is a sensor, and you could see by where the various particles hit, you could get a feeling for your particle population. Mass spectrometers are important in a practical sense because a lot of times when particles are like when you have a particle source, that source is generating a whole bunch of different types of particles, different masses, different charges, that kind of thing. So if you're going to use a particular type of particle for, say, some sort of experiment or laboratory work, you often need to then sort through. You need a particle sorter, and a mass spectrometer is really good for doing that. So that would be one reason we would use these. They're um, kind of an important tool in a lab. So we'll look at the B field region first, right? That's our main topic right now, and that is kind of all laid out in a nice way for us to look at. If we look at that, we see that we have this nice situation. So I'm going to say here, let's focus on the B field region. We have this really nice situation where we have V is perpendicular to B, right? That's nice. And we know that the result from that is circular motion. That's a special case, but it's one that we're given here. So what that tells me is that when I apply my general equation here, if I apply this general vector equation, the magnetic force equals Q vector product V cross B, and I want to find the magnitude of that, right? That's really what I need is magnitude. The directions are kind of given here. That's going to be equal to QVB sine phi. And we see up here that phi is equal to 90 degrees in this case. So sine phi is equal to 1. So this is just equal to QVB, my magnetic force. Nice. So that's kind of easy to work with. And this is circular motion. So I'm going to look at centripetal force here, where I know that mv squared over r then will be equal to, it's the magnetic force that is functioning as our centripetal force is equal to QVB. So just remember that there's no special force that arises out of magic called the centripetal force. Centripetal force is a special term that we use for whatever real physical force is causing a particle to change direction. That's just the term we have for it. So if I ask a student sometimes, like, identify this force, and they say, oh, that's the centripetal force, I will say, you've not identified the force. Every force has needs to be a real physical force, not like an imaginary force, right? So centripetal forces can be caused by lots of things. In this case, by the magnetic field. So the relationship between R and X, if I look at X in my diagram, that would be equal to 2R, right? So here I can say where r is equal to x over 2. So r is actually half of x. So let's go ahead and put that in terms of x there because we're being asked to determine some expression for x. So I'll have here mv squared, and then I'm going to put that over x over 2. So my x ends up down there. I bring my 2 up to the numerator, is equal to qvb. Now I'll go ahead and solve that for x. What I get is x equals 2mv over qb. Cool, but we're not done, right? So m is given, q is given, v is not given, b is given, v is not given. So that's kind of cool. Potential difference, though, is given. So now we need to say, well, okay, x is going to be dependent on how fast that particle is going when it hits the B field. And what's that going to depend on? Well, it's going to depend on that electric field that the particle was accelerated through, right? And that electric field exists because we have an electric potential difference. So now that's what we need to focus on. So let's look at energy since this was given to us in the form of electric potential difference. And I can say that the electric potential energy of the particle initially, that all goes to kinetic energy of the particle. So the particle is, as it's traveling, as it's accelerated through the electric field, and remember this is electric field in here, right? As it's accelerated through the electric field, with the energy changes from electric potential energy into kinetic energy. So that can help us kind of decide on what our next move is here. And remember that electric potential is just really electric potential energy per unit charge, right? Remember, it's that general kind of thing. So that tells me that I can write electric potential energy as the product of potential difference times Q. Cool. So that that helps me out there. I can say then VQ is equal to now kinetic energy. These are conservative forces, 1/2 m v squared. And I can solve that for v, where I get v then is equal to root 2q big V over m. All right, now I can pop that into my expression for x. So I can say that x is equal to 2m over qb multiplied by root 2q fancy v over m. And that simplifies down a little bit. You can see that that would simplify a bit here. 2 over b root 2m potential over q. So pause for just a moment and have a look at this and think about if that makes sense to you. So x, where it ends up there, right? The bigger the x, notice that the first thing I want you to notice is the b that's in the denominator. So what that means is if I increased the value of B field, would X get smaller? And that makes sense. If you increase B, then force increases, and that's going to correspond to a smaller radius, right? More change over time. So other things that are in the numerator, M and V is in the numerator, that also makes sense. That makes sense to me there. The greater V, that is, the more speed that we will have. And then Q, in the denominator there, the greater the charge is, then again, the greater the force will be. Think about QV cross B there. So the more charge, the more force we're going to have, the more force, the tighter turn it's going to make. Therefore, the smaller X will be.